Welcome back, everyone. Around the world, engineers are beginning to explore a promising way to convert vehicle traffic into usable electricity using piezoelectric roads. These systems rely on special materials embedded beneath the road's surface that generate electric current when pressure is applied. Every time a truck or heavy vehicle passes over one of these sections, the force of its weight compresses the piezoelectric layers and produces a small amount of electricity. When scaled up along busy transport corridors, this effect could provide a continuous local power source. From lighting systems to sensors and charging stations, the energy harvested could be used in a variety of ways. Countries including Israel, Italy, and China have already begun trials, and new tests in the United States are focusing on freight routes where heavy loads provide the strongest effect. The basic principle behind piezoelectric roads involves materials that can convert mechanical stress into electric charge. These materials are known as piezoelectric elements and are commonly found in ceramics, crystals, or certain polymers. When they are compressed, squeezed, or otherwise deformed by external forces, the structure of the material shifts in a way that produces a flow of electricity. This property has been studied for decades and is already used in a wide variety of sensors, including microphones, ultrasound machines, and vibration detectors. To apply this concept to roads, engineers embed piezoelectric materials beneath the surface of asphalt or concrete in strips or layers. These embedded modules are positioned where heavy vehicles such as trucks apply pressure during normal travel. As each axle passes over, the weight pushes down on the road and activates the piezoelectric effect. The energy generated is collected through a set of conductors and directed toward nearby energy storage units or directly into the grid if the system is designed for live transfer. A single compression event produces only a small amount of electricity, usually measured in milliwatt or watt scale. However, on busy freight corridors where thousands of trucks pass daily, the combined effect can become substantial. The key to making this system effective is to place the piezoelectric materials in areas with the highest traffic volume and the greatest axle pressure. Heavy trucks and buses offer much more usable energy than passenger vehicles because of their greater weight. The collected energy can be used in several ways, depending on the local infrastructure. In some cases, the electricity powers road lighting, traffic signals, or highway sensors. In other applications, it might be routed to nearby facilities or used to charge batteries for later use. If it's connected to a larger power network, the harvested energy may also reduce local electricity demand by feeding back into the grid. The design goal is always to place energy harvesting close to where it will be consumed, which helps reduce transmission loss. The system must be durable and capable of withstanding extreme weather temperature shifts and repeated pressure cycles. To meet these demands, piezoelectric elements are sealed in rugged, water-resistant casings and embedded below the road surface. Engineers have to ensure that the road remains safe for vehicles, and that installation doesn't interfere with traffic flow. In most cases, the installation can occur during scheduled maintenance or construction, which helps to minimize disruption. Advanced control units manage the electricity generated, monitoring both traffic flow and energy output. These systems allow engineers to calculate efficiency, schedule maintenance, and integrate with smart road infrastructure. By collecting data about road usage and environmental conditions, they can also help optimize the placement of future piezoelectric sections. And when integrated with wireless communication tools, they become part of a broader network of intelligent transport systems. Piezoelectric roads are often combined with energy storage components, such as lithium batteries or supercapacitors. These allow the system to continue delivering power even during off-peak hours when traffic volume is low. Stored energy can be used later for lighting at night or during emergencies. This local buffering capability makes the system more flexible and valuable in regions where consistent traffic flow cannot be guaranteed. Some models of piezoelectric harvesting units are modular and easy to replace. This allows for scalable deployment, where a section of road can be outfitted and then gradually expanded based on performance. Maintenance involves monitoring both the physical wear on the modules and the electrical output over time. If a unit begins to degrade or underperform, it can be replaced without tearing up the entire road surface. Although the energy density of piezoelectric roads is lower than solar panels or wind turbines, their advantage lies in utilizing existing infrastructure. No additional land is required, and no new behavior is expected from drivers. As long as vehicles use the road, power is being generated. This makes it an attractive supplement for urban energy systems, especially in areas where space is limited and demand is growing. One of the most promising applications of piezoelectric technology beyond roads is in rail transport systems. The immense weight and repetitive movement of trains offer an ideal environment for energy harvesting. By installing piezoelectric strips beneath railway ties or alongside the trackbed, engineers can capture energy every time a train passes. This energy can be used to power signalling equipment, station lighting, or onboard systems in a decentralized manner. It may also be valuable for monitoring the health of the tracks themselves, as deviations in pressure patterns can indicate damage or wear in the infrastructure. Rail networks around the world are exploring this technology as part of their shift towards self-powered smart systems. Piezoelectric floors are another emerging application, especially in high-traffic public spaces, such as airports, train stations, and shopping centres. Every step a person takes generates a small amount of mechanical pressure, which can be harnessed through embedded tiles that contain piezoelectric elements. When thousands of people walk over these tiles each day, the accumulated energy can power lighting, signage, or wireless charging stations. This type of system serves as a visible reminder of energy consumption and environmental awareness. Some sports arenas have begun using piezoelectric floors to help offset the cost of their operations during major events. Another field where piezoelectric energy harvesting shows potential is in the design of smart clothing and wearable electronics. Flexible piezoelectric fibers can be woven into fabric to generate electricity from body movement. For example, the motion of walking, running, or even breathing can produce energy that is stored in small onboard batteries. This energy could power sensors, communication devices, or emergency beacons integrated into the garment. Such systems are especially useful for soldiers, rescue workers, or remote field researchers who need power but have limited access to charging infrastructure. As materials science continues to improve, the durability and comfort of piezoelectric textiles are likely to increase, enabling a new generation of self-charging wearable devices. As more governments and companies seek practical energy solutions that do not require new land or extensive infrastructure, piezoelectric roadways are becoming a serious area of interest. The system is silent, passive, and operates in the background of everyday traffic. Once installed, it does not interfere with normal road use and can begin generating power immediately. While the output is not sufficient to replace other energy sources, it offers an efficient way to recover power that would otherwise be lost. If long truck corridors are equipped with this technology in large numbers, they could provide clean electricity for nearby systems without needing solar panels or wind towers. Thank you very much for watching. Please like and subscribe.